Welcome back to Basic Electronics. We now start with a new topic, namely interface between the analog and digital domains. We will look at the basic functionality of a digital to analog converter or DAC. We will then look at a DAC implemented using binary weighted resistors and work out various quantities of interest for an example. Okay, let us begin. We will now discuss analog to digital conversion and digital to analog conversion. And let us begin with the motivation behind this kind of conversion. Why do we need this conversion in the first place? So here are some points. Real signals, for example, a voltage measured with a thermocouple or a speech signal recorded with a microphone, are analog quantities, varying continuously with time. On the other hand, the digital format, as we have seen earlier, offers several advantages such as digital signal processing, storage, use of computers, robust transmission, etc. Therefore, it makes sense to convert these real signals, that is the analog signals, to the digital format and then take advantage of all of these features that the digital format offers. An ADC does just that. An ADC, which stands for analog to digital converter, is used to convert an analog signal to the digital format. Alright. Now the reverse conversion from digital to analog is also required. For example, music stored in a DVD in the digital format must be converted to an analog voltage for playing out on a speaker. That is how we hear that music. And that conversion is done by a DAC. A DAC, which stands for digital to analog converter, is used to convert a digital signal to the analog format. Here is the schematic picture of a DAC, that is digital to analog converter. This is the digital input, that is the analog output. Then we have ground and a reference voltage for the chip. The digital input has n bits, D0, D1, D2 up to Dn minus 1. Now depending on the values of this binary number and this reference voltage, the DAC will produce an analog voltage output. Here is an example. For a 4-bit DAC, that means n is 4 here, with input S3, S2, S1, S0, that corresponds to D3, D2, D1, D0. The output voltage is VA equal to K, some constant, times S3, which can be 1 or 0, times 2 raised to 3, plus S2, which again can be 1 or 0, times 2 raised to 2, plus S1 times 2 raised to 1, plus S0 times 2 raised to 0. And in general, we can write this equation as VA equal to K summation from 0 to n minus 1 Sk times 2 raised to K. So the important thing to notice here is each bit gets a different weight. The higher bits get a higher weight and the lower bits get a lower weight. And this scaling factor K here is proportional to the reference voltage VR, this one. Its value depends on how the DAC is implemented. Okay, now let us look at how VA varies, the output voltage here, as a function of the digital input that we apply to the DAC or DAC. And we will take the same example again where n is 4. So it's a 4-bit DAC. So here is our digital input. The first number is 0000, then 0001, 0010, etc. all the way up to 1111. So this is decimal 0, this is decimal 1, 2, 3, 4, etc. up to 15. And as a result of this applied input, the output voltage VA varies from 0 to some maximum output voltage. And note particularly that we don't have a straight line here or a curve, we have only discrete points, and that is because our input is discrete. We have only these 16 values and nothing between two values. For example, there is no digital input between this number and that number. So that is why we see points here and not lines or curves. Alright, now this difference between two successive output values is called the resolution of the DAC. Knowing the number of bits of the DAC and the maximum output voltage, we can easily figure out the resolution, because we know that there are 2 raised to n minus 1 divisions over here. In this case, for example, we have 2 raised to 4 minus 1, that is 16 minus 1, or 15 divisions between the lowest and the highest values. So then we can calculate the resolution as the maximum output voltage divided by 15 in this case. Let us now talk about implementation of a DAC, and our first approach is to use binary weighted resistors. What is the meaning of this term? If one resistance is R, then the next one is 2 times that is 2R. The next one is 2 times 2R, that is 4R, and then 8R, and so on. Alright, now this specific example is a 4-bit DAC. The inputs are S3, S2, S1, S0. So S3 can be 0 or 1, S2 can be 0 or 1, and so on. The output is VA, the output of this op amp here. We have 4 switches here which are controlled by the input bits S3, S2, S1, S0. This switch, for example, is controlled by S3. If S3 is 0, then this node A3 gets connected to ground, like that. And if S3 is 1, then A3 gets connected to this reference voltage VR. In other words, the voltage at this node is S3 times VR. If S3 is 0, then that voltage is 0. And if S3 is 1, then that voltage is VR. And that is what we have shown over here. And similarly, this switch is controlled by S2, and therefore this voltage is S2 times VR. This one is controlled by S1, therefore this is S1 times VR, and this one is S0 times VR. Okay, so that is our simplified circuit, and we see that it is our op amp summer, and let us now see how that works. Since V minus and V plus are equal, we have V minus equal to 0, and therefore this current can be calculated, and this current is nothing but I0 plus I1 plus I2 plus I3. I0 is S0 VR minus 0 divided by 8R. I1 is S1 VR minus 0 divided by 4R, and so on. So that gives us this expression here. So the current I is S0 VR by 8R plus S1 VR by 4R, etc. And now what we can do is to take this VR by 8R common and then get this expression here. Now here we have written a general expression for n bits. In our case, n is equal to 4. So this 2 raised to n minus 1 is in our case 2 raised to 3, which is the same as 8. So this is what we get, and as we expect, each bit gets a different weight. For example, the LSB S0 gets a weight of 2 raised to 0 or 1, and the MSB S3 in our case gets a weight of 2 raised to 3 or 8, and that is what we would expect from a DAC. Finally, let us find the output voltage VA here, and we have done that earlier when we talked about op-amp circuits. This V minus is 0 volts and there is no current going into the op-amp. Therefore, this current I also goes through RF, and therefore VA, which is our output voltage VO, is 0 minus I times RF, and that is what we have over here, minus RF times I, and I comes from this expression, and therefore this is what we get for the output voltage. Let us take a specific example. Consider an 8-bit DAC with VR equal to 5 volts. What is the smallest value of R, that resistance, which will limit the current drawn from the supply to 10 milliamps? This is our supply VR, and that is supplying all these currents, and the total current that we draw from the supply should be limited to 10 milliamps. Now, since this is an 8-bit DAC, our resistance values go from R, 2R, 4R, etc. Then 2 raised to 6R, and the last value is 2 raised to 7R. Otherwise, the circuit is the same as what we saw earlier. We have a total of 8 switches now in the circuit. This switch is controlled by the LSB, that is S0. This switch is controlled by S1, and so on. And finally, this switch is controlled by S7, which is the MSB. Now let us look at these currents, I0, I1, etc. up to I7. Now this node is at virtual ground. V minus and V plus are nearly equal. So therefore we have 0 volts here. This current I0 is given by the potential at this node A0 minus 0 divided by R0, which is 2 raised to 7 R. And similarly, we can get these other currents. When S0 is 0, this switch is in this position. Node A0 is at ground, and therefore I0 would be 0. On the other hand, if S0 is 1, then the switch is in that position. The potential here is VR, and then we do have a current VR divided by R0. In other words, this resistor is drawing a current from the power supply only if S0 is 1. Similarly, this resistor will draw a current from the power supply if S1 is 1. And for the power supply to supply the maximum current, clearly we require S0 equal to 1, S1 equal to 1, etc. all the way up to S7 equal to 1. So that is what we have written over here. Maximum current is drawn from VR when the input is 1, 1, 1, 1, 1, 1, 1, 1. That is, all nodes A0 to A7 get connected to VR. Alright, and that maximum current is restricted to 10 milliamps. So therefore we equate 10 milliamps to VR by R, that is the current through this resistance, plus VR by 2R, the current through the next resistance, and so on, all the way up to VR by 2 raised to 7R, that is this current. And we can take VR by 2 raised to 7R common and get 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2, etc. up to 2 raised to 7. And this bracket turns out to be 2 raised to 8 minus 1, that is 256 minus 1. 2 raised to 7 is 128, so therefore we end up with 255 by 128 times VR by R, and that should not exceed 10 milliamps, and that gives us the value of R, the minimum value of R. So that is VR, which is 5 volts, divided by 10 milliamps times 255 by 128, and that turns out to be about 1 kilo ohms. Okay. Now this example has been taken from this book by Gopalan, and it has many other interesting details about DACs and ADCs, and it's a good book to look at. Next question, if RF is equal to R, what is the resolution, that is delta VA, change in VA here, corresponding to the input LSB changing from 0 to 1 with all other input bits kept constant. Alright, so this is our expression for VA, and this bracket corresponds to the input binary number. What is the lowest value of this bracket? That happens when S0 is 0, S1 is 0, etc. all the way up to S7 equal to 0. So that lowest value is 0. What is the highest value? Highest value is when S0 is 1, S1 is 1, etc. all the way up to S7 is 1. And that highest value is 255, or 2 raised to 8 minus 1. And when we talk about resolution, what it means is we are allowing a change in this bracket by 1. And that is the same as saying that it is delta VA corresponding to the input LSB, this S0 here, changing from 0 to 1 with other input bits constant. Okay, we can now calculate the resolution. So the resolution, which is delta VA when this bracket changes by 1, is given by this factor here, which is reproduced here, and that is 5 volts, that is VR, 2 raised to 8 minus 1, this number here, times RF by R, and RF and R are assumed to be equal, so therefore this turns out to be 0.0391 volts or 39.1 millivolts. Next question, what is the maximum output voltage in magnitude? Here is our VA, and note that it is negative, and that is why we have put magnitude in brackets over here. And when does the magnitude become maximum? That happens when the bracket becomes maximum. That means all these bits are equal to 1. So the maximum VA in magnitude is obtained when the input binary number is 11111111. So all we need to do now is to replace all these S's by 1 and evaluate this bracket, and that is what we get. VR is 5 volts, 2 raised to n minus 1 is 128, RF and R are equal, so that is 1, and this bracket is then 2 raised to 0 plus 2 raised to 1 all the way up to 2 raised to 7, and when we evaluate that we get 9.961 volts. Next, find the output voltage corresponding to the input binary number 10101101. Fairly straightforward to do. We have VA here. All we need to do now is to put S7 equal to 1, S6 equal to 0, S5 equal to 1, S4 equal to 0, and so on. And that is what we get. So VA turns out to be minus 6.758 volts. Next question, if the resistors are specified to have a tolerance of 1%, what is the range of mod VA corresponding to the input 11111111? Alright, now first let us figure out what this means, a tolerance of 1%. Take this resistance for example, let us say its nominal value is 1K. Then what this means is that the actual value can be anything between 0.99 times 1K to 1.01 times 1K. What about this resistance? We will assume that R and RF are the same, so therefore the nominal value of R7 is also 1K, and therefore the actual value will vary from 0.99K to 1.01K. What about this resistance? Its nominal value is 2 raised to 6 times R, that means 64 times 1K or 64K, and its actual value can vary from 64K times 0.99 to 64K times 1.01. Okay, let us now get back to our original question, and with this input all our switches are in the upper position. That means A7 is connected to VR, A1 is connected to VR, etc. And all of these currents now are non-zero. Now for VA to be maximum in magnitude, all of these currents must take on their maximum values, and that happens when these resistances take on their minimum values. That is condition number 1. Second condition is that this current, which is addition of all of these currents, now passes through this RF, and this RF times I should also take on its maximum value. That means RF should take its maximum value. Once we realize that, then it's straightforward to calculate VA max. So mod VA is maximum when A, currents I0, I1, etc. assume their maximum values, with RK equal to RK0, that is the nominal value, times 1 minus 0.01, that is 0.99. So the resistances, these resistances take on their minimum values. That's how these currents become maximum. And second, RF is maximum, that is RF is equal to its nominal value times 1.01. So the maximum value of mod VA for this condition is then PR times 255 by 128, this we have seen earlier, times the maximum value of this ratio, RF by R. That means 1.01 divided by 0.99. Because their nominal values are equal, they cancel out, and that gives us 10.162 volts. What about the minimum value of mod VA? That is just the opposite. We want to make this number now as small as possible. So RF should take on its lowest value, and all these resistances should take on their maximum values. So that gives us this same factor times 0.99 divided by 1.01, that is 9.764 volts. So as we found in the last slide, for a fixed input combination such as 1111, 1111, the output voltage can vary substantially because our resistances are not perfect, they have a non-zero tolerance. And in the last example, we found that the maximum VA in magnitude was 10.162 and the minimum was 9.764. And the difference between these two is about 0.4 volts, which is quite significant because it is much larger than the resolution of the DAC, which was 39 millivolts. So this situation is clearly not acceptable because it will lead to inaccuracies. And what can we do to improve this situation? We can use resistances with a more tight tolerance. So the output voltage variation can be reduced by using resistors with a smaller tolerance. However, it is difficult to fabricate an IC with widely varying resistance values such as R to 128 times R, and each with a small enough tolerance. So there is a technological difficulty there, and therefore this entire design needs to be improved upon. The solution is to use the so-called R2R ladder network. In this network, we have only two resistance values, R and 2R. So all resistors in this network will be either R or 2R. And in this manner, this problem of delta VA arising out of variation in resistance values gets effectively addressed. To summarize, we have started looking at digital to analog converters. We looked at an implementation using the binary weighted resistor approach. We considered an 8-bit DAC example and worked out various quantities of interest. We found that statistical variations in resistance values makes this type of ADC unsuitable when the number of bits is large. In the next class, we will look at the R2R ladder approach, which circumvents this difficulty. See you next time.